Good morning, everyone. My name is Saiteja from ECC section. Today, my topic is scale up or scale out for graph processing. Introduction. Whether we should scale up or scale or out for graph processing is an consequent question for the two perspectives. For big data practitioner, it would be desirable to develop a set of best practices that provide guidance to organize building and developing graph processing capability for big data researchers. This best practice translates into priorities for the future work and provide a roadmap prioritizing real world pain points. I advocate scale up solution for graph processing as the first thing to try, since they are much simpler to design, implement, deploy, and maintain. If you really need distributed scale out solution, it means they can organization has become immensely successful, not just successful but on growth trajectory that it outpacing Moore's law. This is unlikely to the case for most organizations, and even if you were fortunate enough to experience such explosive growth, such success would likely bring commensurate research to throw at the problem. So, as long as you leave yourself enough headroom, it should be possible to build a scale up graph processing solution just in time. The alternative is sunk cost in distributed graph processing infrastructure, which causes the huge parallelization overhead, anticipating a problem that never arrives. It makes sense to begin by more careful describing the scope of the problem. The type of graph processing I am referring to involves analytical queries to extract insights or to power data products. An example for the former might be clustering a large social network to interfere in land communication for interest. An example of latter might be building a graph based recommendation system. Typically, these queries require transferring large portion of the graph where throughout not latency is the more important performance consideration. Gather defines operational database as relational and non-relational DBMS products suitable for a broad range of enterprise level transaction application, and DBMS products supporting interaction and observation as alternative type of transaction. I am specifically not referring to this, for example, user facing system that store and serve a large graph such as Facebook TAO. WTF at Twitter. Previously, reader of the column known that my opinion was strongly colored by in the terrains. Experience working full time at Twitter from 2010 to 2012 on building infrastructure to support data science and platforming to power data product. For graphing process, Twitter has been an adopt of scale of approaches, starting with the first graph based user recommendation project called WTF, who to follow. Present a more technical version of story, but there I provide a summary of relevant design rationale. The WTF project began in spring of 2010 as an effort to plug a gap in Twitter product of fearing. At the time, Facebook and LinkedIn already have mature user recommendation service, but Twitter has no comparable features to suggest account user might be interested in following. The short time to market with important goal for the perspective. WTF was a great success. It launched later that summer. The single biggest contribution factor to this rapid development, I believed, was the archi- architectural design to hold the entire graph in memory or on a single serve, implemented in an open source graph processing engine called Cassowary. This design were much went against the grain of conventional wisdom, which held horizontally scalable distributed system as the gold standard. Why did we reach this contrarious decision? The design choice broke down into two separate considerations. First, did the graph fit into memory? In this case, the graph of interest was the network of follow relation on Twitter. Although many other graphs existed for which recommendation could be computed, such as induced for engagement, replace like retweet, etc. Leveraging the follow graph seemed like the obvious starting point. This was a simple and straightforward question to answer, even with the most ineffective encoding of uncompromised source destination pairs. Each graph edge consumes 8 bits, which translates, for example, into 64 GB for a graph with 8 billion edges. Based on statistics at that time, the question to these answers was yes. Second, how much headroom or runway did we have? That is factoring an anticipated growth, how much time until we run out of memory. Based on historic data, it is possible to run projection of graph size over time under different assumptions. And for the projection, it was straightforward to design an answer. Crucially, this project accounted for Moore's laws. That is, even if we didn't nothing. In roughly 18 months, Moore's law would give us serves with double amount of memory. We consider ourselves that a sufficient headroom to provide the scale-up design. WTF launched an service with 72 GB RAM and as planned later moved to server with 144 GB RAM. Imitation as flattery. It is clear that scale-up design philosophy has a large impact of Twitter. Even the scale-up architecture were eventually preferred. Simply throw more memory at the problem was never summarized dismissed without a careful consideration of the engineering and product merits. They were beyond Twitter. In March 2017, 7 years after the original WTF project, Pinterest publishes the following blog post with Pixie, that graph-based recommendation system. The blog post does on the explain how Pixie powers recommendation across Pinterest and accounts for about half of all pin saved. Survey says so far this discussion has mostly focused on graph-based recommendation algorithm. For my personal experience, looking more broadly, what do users want from graph processing software? What type of graph data do users have? What computations do users run on these graphs? What software do users use to perform these computations? What are the major challenges user faces when processing their graph data? The graph size questions were formulated as discrete range that participants could select from the largest value provided were 1 billion edges and 100 million vertices respectively. Therefore, the survey results are unable to tell us how much larger these graphs actually are. How many trillion edge graphs are there at the low end? Though these graphs still aren't that big, 1 billion edges as pairs translate into 8 GB with less brain encoding. Such a graph easily fit into a memory on a laptop today. A graph with 100 billion edges, even with a moderate amount of metadata, could com- comfortably fit into the memory on a commodity service today. Conclusion: if there are solid case for scale up as a variable alternative to scale out for graph processing, then we haven't have more organization consider that alternative. I propose two explanations. First, I believe that a fundamental level humans have difficult reasoning about exponential growth and basic line characterized by exponential growth. For example, we When we hear about an investment fund manager who have achieved impressive returns over the last 10 years, most people initially reaction is not to ask about the returns of a well deserved index fund over the small time period. As a concrete example, a number of years ago I asked some Cloredra colleague why so much effort was being expended in developing HDFS name node failover mechanisms, some of which were really closely in my way. In my view, the amount of engineering research devoted to tackling the problem was disproportionately more the reality of the problem. I thought there were far away more pressing pain point in Hadoop ecosystem. The response I got was essentially that point here process which write the checks need to make sure that the highly available no spoof square their buzzword bingo cards were was covered. Deploying an inconvenienced distributed scale out graph processing system is dangerous. First, as McSherry showed, organizations need to throw a lot of resources on digging themselves out of the hole there were system created in the first place. At the end of the day, spec- significant research has been sunk anticipating growth they may never actually materialize. They are the course organization. For example, Facebook and Google, they genuinely need a scale out graph processing, but it isn't the common case by far. Better to start with scale up solution for graph processing. Thank you.